officially started.
Cool, great. All right. Well, yeah, thanks everyone for joining this session on AI native battery engineering. Yeah, I'll just start by introducing myself and Liam, and then we'll dive straight into it. But to give you a bit of the agenda for this session, I've kind of got like 10 minutes where I'm going to talk at you with some slides just for background, so we're all on the kind of same page. And then I'm going to have some live demos. I'm going to ask you to vote about which of those you'd like to see most. We might have time for both, depending on how many questions we have. Then I will save kind of like half the time at the end just for a discussion around this topic. So please interrupt me, shout out if you have any questions. Keep this pretty informal as we go through. Keen to hear people's thoughts on this. But anyway, I'm Rob Timms. I'm co-founder and CTO at Ionworks. We're a battery software company. I'm also a core developer of PyBAM, which is an open source battery simulation software that those of you in the sort of modeling and simulation space may be familiar with. Liam, I'll let you introduce yourself.
Sure, sure. Liam Cooney. I head up sort of the business and commercial side of the house at Ironworks. My background is both on the development and manufacturing of batteries, and then also different software systems that have supported those efforts throughout the years. So, like Rob said, any questions, feel free to holler out at any time. And Yen has messaged me to remind everyone to, if you feel comfortable enough, to turn the cameras on. And if you can put your organizations like next to your names. But other than that, I'll hand it back to Rob to start.
Cool, great. Thanks, Liam. So yeah, this is a talk on AI native engineering. So how do we embed AI into engineering practices? And the particular focus of this session is going to be on using the right tool for the job. So what I mean by that is, in the context of battery modeling, is how do I use the right battery model to answer the question that I really care about answering? Have I got the right data to build that model and answer the question that I care about? And how do I develop a workflow that I can use to do that in a reproducible way that's suitable for humans and AI agents? So there are lots of questions you can answer with modeling and battery models in particular, and they can be sort of simple questions and they can be very difficult questions. And depending on what you're trying to get out of the answer depends or dictates which model you might want to use. So maybe one of the simplest things you could think of trying to understand with a model is, I'd like to predict the voltage response under some given profile. And so there, a simple empirical model might be enough for you, or an equivalent circuit model, because really you just care about voltage prediction. Maybe here, like, root mean square and voltage is like the biggest thing you care about. And ECMs are very good at doing that. But there are other classes of questions that you might like to ask yourself as well. And they might be around operating conditions. So this could be, how can I do a fast charge without plating lithium? Or there might be design questions. So if I've got some KPI that I'd like to hit with a particular cell, something like power, energy density, lifetime, whatever that may be, can I use a model to understand what design trade-offs I can make to help me hit that KPI? And obviously, for those second two questions, you're going to need a very different kind of model, because those questions require you to either have some insight into internal states. If you're looking at lithium plating, you might want to track the anode potential, for example, or they require you to have some kind of link between design parameters that maybe you care about in manufacturing or cell design. So these might be thicknesses, loadings, porosities, etc., and how they link to cell performance. And so the question I want to answer today is, how do we standardize decisions and workflows around answering these kind of questions, in order that we can pick the correct model, parameterize it appropriately, validate it, and use it to answer the question that you care about? So the workflow for this, if you're starting a battery modeling project, might look something like this. So you come up with some question that you're trying to answer, and then you have to ask yourself, which model do I use? Once you've answered that question, you have to ask yourself, do we already have this model available to us within our organization? And if we do, that's great. We can go ahead and use that model, run some simulations to help us answer the question that I care about. If we don't, we then have to ask ourselves, do we have the data required to build the model that we need? And if we do, then we can go ahead and parameterize that model and then run the model again. And if we don't, then we need to flag that we can't actually answer the question that we want to answer with the current data and modeling framework we've got available. And so at that point, we then need to either ask a different question or think about doing something else, like collecting different data. And the goal is to make this fast, easy, and reproducible within an organization. And eventually, when we get towards the end of this talk, how we can connect this into AI agents so that we can really accelerate this whole process and do this in a really systematic and streamlined way. So the first step is which model to use. And here's a quote that everyone's probably bored of by now, but I think the reason we're so bored of it is because it's just such a correct quote. All models are wrong and some are useful. And this comes back to the question we had earlier. If you care about uh, just getting voltage predictions, then maybe the thing you want is the most accurate model at the lowest voltage error. But perhaps that's not actually useful at all for the question you're trying to answer. And you might prefer to have a model that's got more error in it versus your validation data, but gives you the insight that you need. And somehow you need to encode this into your decision-making workflow. So, what decisions am I wanting to support? What am I trying to answer? And what data do I have for this cell? And what can I realistically collect? And so the decision matrix for choosing this model might look a little bit more complicated, something like this. So you might start by saying, what's the decision that I'm trying to make? So this could be a voltage prediction, this could be internal state design, could be cell design optimization. And then what kind of data do I have? Have I got teardown data, for example? Have I got half cells? If I haven't got that, that limits the amount of models I can make. If I have got teardown data, then I can. And so what this might look like in practice, even if you're not using AI in your organization, is you've probably got some knowledge base somewhere within your organization that people can contribute to, and you can encode all this information in some unified place. So before I go on to the next part of the talk, there's two workflows that I'm going to demo, or at least one of these I'll demo later on in the Ionworks platform. One of these is an equivalent circuit workflow. And so this might be something like, I've got some Arbian schedules that I'm going to run on a bunch of LG cells that I've got. But before I want to do this, I want to simulate this profile to make sure that I've not got any problems with my protocol, or I want to estimate a realistic duration for that. And so we're going to use this decision matrix to say, what model do I need? What data do I need? What's the plan for doing that? And then the second one is one that's more geared towards physics-based modeling. So here you're looking at designing a 21700 form factor cell and trying to play with electrode loading to see how that influences the discharge capacity of the cell at different rates. And so, yeah, I haven't started a proper poll in Zoom, but maybe if you can sort of comment in the chat box which of these you're most interested in seeing, and I'll prioritize doing that one first. So once you've made your selection about the kind of model that you want to do, you need to parameterize this model. And so here, again, you need to encode some kind of best practices. One way of thinking about this is to think about these four pillars, best practices for parameterization. So the first one is kind of straightforward. It's the steps. So given a model that I want to try and parameterize, what do I actually do to parameterize the model? What data do I need? What is the sequence of going from data to final model? But what you also want to build into this process are some kind of gates. So at each step of that parameterization process, I might have some checks on, is my error acceptable? Is the model making physically reasonable predictions about things? And so these gates allow you to make sure that you're not getting too far through the process, where you might have some bad model getting introduced because you've not got the right data early on, and that doesn't get picked up until way further down the line. And so what having these gates that you do is have some branches. So if you fail a gate, it's another chance to make a decision. What do I do? Can I substitute in some different data? Can I build a different model? What are my options here? And then you need to be able at some point to say, when do I need to exit? So what happens when I get to a point where I say, I can't actually build a model that I need to build to answer the question that I want or meet the error threshold that I care about? So what should I do? Should I change my model? Should I change the scope of my question? Should I go back and require actually that I need to collect some more data because this decision really is critical and I need this model to make this decision? And so one example of a parameterization workflow might look something like this. This is fairly standard if you're familiar with doing this kind of work or you've read the literature on physics-based model parameterization. So here on this diagram, we've got data coming in from different sources in the blue and some kind of process in the yellow. So I might collect half cell data of open circuit potentials, do some electrode balancing, fit some dynamic profiles like GITT to get diffusion coefficients, bring in that teardown information, and so on. And this workflow would look different depending on which kind of model I'm going to build and which data I've got available to build to that. And again, in practice, you encode this in some kind of knowledge base within your organization, and this might be manually maintained by humans. So we're going to see some worked examples of this later on, so I won't dwell on these two slides, but what I'm going to show in these worked examples is, how we go through this decision of what's my application, what data do I need, what's the plan for doing that. And so the goal really, when we think about bringing AI to this is, can we improve the efficiency of this process? And not only can we improve the efficiency, but can we make sure that we're constantly learning from this? what can quite often happen is if you've got these manual knowledge bases and you've got work being done by individual engineers, is that someone learns something in the process of doing this, and that never makes its way back into the knowledge base because you have to manually update that. And so what we really want is like a self-improving framework where our knowledge base is improving over time as we're doing more and more of this type of work, and we see different edge cases that perhaps we haven't encountered before. So just to make sure we're all on the same page when we talk about AI agents, there's a few different flavors of things that might come to mind when you think about AI. One is classical machine learning. So these are sort of statistical and optimization techniques, linear regression, model-based approaches. There's deep learning that may come to mind. So sort of neural networks learn representations from data. What we're really talking about in this talk is agentic AI. So these are large language models, but enhanced with tools and that can reason over the questions you're asking them and use those tools to effectively make a decision. So with a classical LLM, you just give it a prompt, can you do this? And it gives you a response, yes, here's what I did. With agentic AI, you give it a prompt, it's going to look at the tools that are available to it. It's going to run those tools, interpret what it did, see if it needs to update the prompt and go back, and it can sort of update this prompt iteratively in this loop until it's able to configure the right tools and get the right outputs it needs to get the result that you're asking it for. And so, those first two parts that I talked about, those knowledge bases, those decision matrices, they can happen without AI, they can be human things. What's really useful is, when you've got that agent can walk that same matrix, that same knowledge base, and then make tool calls in order to do this. And that's what we're building at Ionworks, is the API to give agentic AI the right tools to be able to make these kind of battery modeling decisions and query data in the appropriate way. So I'm going to try and take a look at chat now if I can find where it brings it up, or maybe Liam, you can do it on my behalf because
Yeah,
I can't find the
limited
right screen.
response, but it looks like physics-based is where people want it to start.
Cool. Great. So I'm just going to pull up my other screen now. Let's see if it'll let me switch here. Here we go. Cool. So hopefully now you're seeing the Ironworks platform. So this is the web front end for the Ironworks tools, Ironworks Studio. This is also just an API. So for those of you who prefer just coding directly in Claude or Copilot, whatever you like to use, you can do exactly the same kind of thing using your AI tool of choice. So I'm just going to jump into this agent demo project. And the way our framework is organized is that you have cells. So I've got some cells that I've included here. So this is like some particular class of cell, and I might have many instances of this cell that correspond to an actual physical cell, and they have data and materials associated with them. And what we'll see later on is that we can build models within this framework, and then use those to do simulations or design optimizations. And so I'm going to start then with the physics-based demo, and then if we have time, we can go back and do the ECM one. So in order to do this physics-based demo, I'm going to jump into this cell that I've got in here. So it's just some NMC graphite pouch cell, relatively generic. And I've got some corresponding half cells in here that correspond to these materials I've made. And this is all linked in this database. So I'm going to hop over to this cell, and I can see I've got some data associated with that. So I can take a look at that data in the platform. Okay, and that's a very long time series trace, so you probably wouldn't plot it like that, but you can do things versus cycle number, for example. And so I'm just going to pull up the agent. I'm going to say, what model can I build from this cell and the associated half cells? And so this is this first part of the decision matrix now. I want to say like, oh, I've collected some data. Maybe it wasn't even me who collected this data. Someone else has collected it. It's dropped in the platform. And now as a modeling engineer, I want to say, I've been tasked with coming up with some answers to some problem like we saw. I want to do a sweep over loading and see how that changes performance. So first of all is I'm going to query the database and see what data I've got available for this cell. And now the agent is going to walk through the skills to parameterize this. This is this knowledge base to understand and query if I've got the right data to build. So it's found this measurement that I'm looking at. It's going to just trace back up to this spec that we were in and see all the data that I've got and the half cells. And it's also going to check to see if I've got things like information about electrogeometry, particle radius, loading, etc. So right now it's just inspecting this information on the database. So let's see. So it's gone ahead and found the geometry. So now I'm just going to take a look at the different data that we've got. And so as it's doing this, it's now just checking against this decision matrix to see if we've got the data required to build a model. And now it's just going to go back and check that it's linked these half cells appropriately and to check that we've got these half cell ACVs. And so this physics-based one's a little bit more involved. So the ECM one gets you to a solution quicker because the decision matrix is a bit smaller here. It's got to do a lot more searching around just to check it's got the data that you've got, the required data. And so what's nice about this is that, okay, so here it's found it, but you can encode, we've got our information encoded in this, but you can bring your own knowledge to this. And so here it's found some information. And so it's given me a list of models that I might like to build with this. So I've got enough data here now to build, an equivalent circuit model, a lumped physics-based model or a full physics-based model. Don't worry too much about the distinction between these two if you're not familiar with this terminology. But essentially, it's gone through. We can see it's found all of the information about these cells and the associated half cells. It's found that I've got OCV, I've got EIS, GITT. So it's saying I've got enough data. So what I'm going to do now is I'm going to say, what steps would you take to build this model? And I'm going to get it to lay out what would be the plan to actually go ahead and parameterize this model. I'm not going to do the parameterization live in this session just because the physics-based one's reasonably involved and it's got a lot of steps to watch through live, but I'm going to get it to lay out what it would do, and then I've prepared the results of this process in another page. So here now it says, I'm going to pull up the fit pipeline that I use for a physics-based model. I go through, and it's giving me all of these steps. So it's got a clear plan for what it would like to do. And it also confirms, is this actually the model I want to build? So something you might do is you might just think, I'm going to go ahead and build the most complicated model I can, because why not? And we can encode in the knowledge base that it can prompt you to say, actually, hold on a minute, maybe a simpler model is more appropriate for what you're trying to do. So it's giving me the plan. It's telling me which data it's going to use to do each of these different pieces of the fits. It's got some gates in. It's going to check, for example, at the electrode balance, that the OCV and the DQDV is aligned properly, and the MP ratio is consistent with the data I've got from teardown. And so everywhere it's got some steps and it's going to go through. And so now if I did want to do this, I could say, go ahead and do this. And this would now, the agent would go ahead and collect all this data, do this parameterization workflow, make sure it passed the gates, and build this model for me. And the output of that would be a parameterized model. So if I just close this for a moment. So within the Ionworks framework, you've got a library of the models that you made. So here's some I've got just from running this demo earlier, but I'm going to pull up this physics-based model of an NMC and graphite cell. And so you can go into this and you can see, okay, this was a PyBand model that I built. I can go in and see different parameter values that I've got. So I can take a look at OCV, for example, and query all these parameters. And so now I'm going to open this agent and now I'm going to ask it the question that we were trying to answer at the start of the demo. So I'm going to say, using this model, what do I do? I'm going to sweep over electrode thickness. I'm going to scale both electrodes by the same amount, but account for different winding length, which is the same as changing electrode width in a 21700 form factor. So what I want to do here is say, I've putting this into some form factor. I want to just keep the MP ratio fixed in terms of thickness, but I'm going to scale over the total thickness of the electrode sandwich stack, but keep within this can. And so it's going to change the amount of windings within the can as I change the thickness. And then I want to say run constant current discharge at a range of C rates from, let's say, C over 2 to 5C. Oops. And plot discharge capacity versus thickness scale factor. And so this might be the kind of thing, if you're familiar with doing modeling and simulation, you could set this up in PyBam or Console or whatever your tool of choice is. But what we can do now is you can ask higher level questions and it's going to go away and configure all of this setup for you. It's going to configure the simulation, make sure it's robust, and generate all the outputs that you care about. So now this is going to go ahead and it's going to grab this model from this page that I'm on, and it's going to think about what simulation setup I need to do. So it's got to do a little bit of work here, right? It can't just take this model and run some simulations. It needs to think about, I need to introduce this scaling factor in the parameter. I need to do some algebra about if I've got a fixed can size and I'm changing electrode thicknesses, that's going to change how the winding how many windings I can get within that can. And so it's going to bring up all of that logic that it needs to do in order to set up these template simulations. And then once it's done that, it can go ahead and run this sweep and then generate this plot for me. And as well as generating the plot, it will do some analysis for me, and then I can ask it further questions. So let's just
Rob,
give it
while
a
we're
little bit of
waiting for
time.
that, looks like there's a couple of questions
Okay,
in the
great.
chat.
Let me see if I can find
The first one
where
is
the chat has gone.
which AI are used?
Yeah, so right now this is hooked up to Claude, but yeah, the framework itself is like based around skills. So in principle, you could bring your own AI to this. The agent within the web that we're seeing here is using Claude. Um,
And then the second one here, which is always the $60,000 question. Can the agent also parameterize mechanical and aging parameters from calendric or cyclic data?
yeah, I mean, so there's two questions to answer there. I mean, around aging, like the academic literature itself still is like, I would say, reasonably young in where it is in terms of accurately parameterizing these mechanistic based models for like SEI, lithium plating, whatever that may be. Um, but yeah, you can encode that knowledge into this. So we've got some best practices around some work we've done on parameterizing these kind of degradation models. And in principle, if you can write the knowledge base that says like, here's the data that you need to do this, here's the steps you need to take to parameterize models, then the agent can reason over that and do it. And so yeah, it's as good as the knowledge base is and as good as the data that's available is. Hopefully that answers that
Cool.
question.
That's it. Yeah, that's
That's
it for
it.
now.
Cool. Perfect. I'll let you read out questions because I've completely lost the Zoom
Yeah,
chat
no
box.
worries. That's what I'm here
Uh,
for.
cool. So yeah, what we can see is this has run this. It's set up and run this simulation for me. Maybe I can just make this a bit bigger. And so, we get kind of perhaps what we expected. So at lower rates, as we increase the thicknesses, we increase capacity. But then when you push these higher rates, at some point your electrodes are too thick. And so you get bigger over potentials from having these very thick electrodes at high rates. And so not only does it generate this plot for us, it can tabulate the data for us, and store all this results for us to reference later on, and also give us some analysis based on this. So yeah, it can give us analysis exactly what it says. So at low rates, we can keep increasing things as much as we like. At high rates, we get some trade-off now due to polarization. And so that's the kind of thing we can use this framework to do. So I think at that point, I'm going to stop there and just see if there's any more questions that have come up on this or just in general about this kind of workflow. We've got sort of like, 15, 20 minutes left. And then if we've got time, I can go back and show you the equivalent circuit demonstration.
Okay, looks like we got one more that popped up in the chat here. It says, when an agent parameterizes from cycler data, does it return uncertainties or a sensitivity ranking?
Yeah, so that's something that's built into the Ironworks tool. So there's many aspects that are connected up within Ironworks Studio. So part of it is the sort of data management that I was showing you where we can see the data. And then another part is building pipelines. And so as part of the optimization process, you can obviously get the fits, and we've hooked up a bunch of different optimization libraries for doing that with, but you can also get uncertainties around parameters or sensitivity analysis. So this is completely hooked up to kind of like the Ironworks parameterization toolkit.
Okay, a couple more here. First one, and I'll take it one at a time. In terms of simulations, do the agents focus purely on electrochemical models or also on data-driven slash physics-informed ML models?
Yeah, so right now within our framework, the models themselves are equivalent circuit models or physics-based models. Um, Basically, when you bring a model to Ironworks, the easiest way to add a new model is you can configure a PyBAM model, or if you're familiar with PyBAM, you can basically make a custom model in here. And so that kind of puts you in the ballpark of equivalent circuit physics-based models. Um, but that's not necessarily like a limitation of the agentic AI workflow itself. That's more the tool that it's hooked up to. So yeah, in principle, if you've got those models available to you to run, then these kind of agentic workflows could be hooked up to that.
Now they're starting to come in. Can you comment on the token usage for the prompts and for the agents doing these tasks? Have we done any work on optimizing this workflow to minimize the token use, to maximize the correctness and reduce false positives?
Um, I haven't got like a hard benchmarking number for you right now, but we have done some work specifically around like how you set up the skills for these like specific tasks, like parameterization, like oh, I'm getting this piece of this parameter from this GIT data or whatever. And there's some things you can do around there to really like streamline or like force the agent into doing something very specific with these tool calls versus just sort of wandering aimlessly around, which is what can end up spending lots of token because you give it kind of like a lot of freedom to try different things. Whereas if you can force it to be very like direct and small in scope at each step of what it's doing, that can help you reduce that token usage.
Yeah. All right. Is it also possible to do material comparison with the agent? For example, NMC versus LFP for a fixed cell type in geometry.
Yeah, exactly. So that would be a case where essentially, um, it's extra skills to teach agent, but that would be an example of running a simulation. So one thing you can do, within this framework itself is you can run studies. And so in here, I might have some new simulation. Um, and so I can configure whatever experimental protocol I might like. Let me see if I can find an example one. There you go. So yeah, I might be doing some CCTV or something. And so all of this kind of thing, the agent can configure as well. So I could say, oh, set me up this simulation of a NMC cell, set me up this simulation using LFP. Or yeah, if you've got the library of materials, you could build models with those two different cathodes and then do that comparison. So essentially, yeah, we're just giving it the skills to be able to like make calls to PyBAM and to the Ironworks framework. So that was a very long-winded way of saying yes.
I think the last question we've got for now is, do you have ways to troubleshoot if the models are not working well?
Yeah, so this part of that. So what we saw today was the parameterization. I think I've got time to go through the ECM one as well. But there's also
Yeah.
like validation skills built into this. So part of that is saying, okay, I'm going to validate this model on some additional data, and it can look at the outputs of validation and sort of say, where is this model not performing well? And also say, where is this model doing something that perhaps is not physical or like there's a big gap between model and data. And in some cases, depending on what that is, it's able to suggest to you where it thinks that might be wrong. Um, I'll do the ECM demo, I think, just because that's a nice case where it does come up with this kind of prompt to say like, oh,
Yeah.
the model's not super good here. Here's something else you could try. Cool. But
Yeah,
yeah,
while
please
you're
keep.
pulling that up, I think it's worth saying too that we've shown like one avenue within the software today, or maybe two avenues within the software. There's obviously much that we're not going to get into on this, but happy to show people like longer demos and give the full breadth of what the software is sort of built to do, both from like an agent standpoint, but then also just as like an engineer or a scientist who wants to use it uh as they would another like piece of software.
Yeah, absolutely. Okay, cool. So yeah, I'm going to start a new chat now with this. So I'm going to ask it the same question again. So now I've got a different cell specification I'm looking at. I've got this LG 18650 cell, and I can see I've got some data associated with this. So I'm going to ask it the same question before, what model can I build with this cell? And so now it's going to go ahead and do the same thing it did before. It's going to query the data that I've got in here. With a smaller amount of data this time, so hopefully it should be a little bit quicker in just taking a look at what's going on here. So it's going to pull up this skill and inventory the data. And then what we're going to do is ask it to build an ECM model doing this, and then we're going to do some validation and get some of this sort of model troubleshooting going on. Also, I've just thinking that's what is the data. So the data for this demo is it's just some open source 18650 like drive cycle data. So if I can minimize that. So yeah, it's like a drive cycle, repeated drive cycle like this, or there's some additional, oops, having some thinking time. There's some additional drive cycle data, which it will pull up in a second. If that's on the go slow, just inventorying this spec to see what's going on. Let's refresh this and see if we can speed it up. Something's hanging for some reason. The live demo is always smooth.
Always the best.
Yeah, let's just go back here. If in doubt, just reset and start again.
Yeah, turn it off and turn it on again.
So let's try again. What model can I build with this? So hopefully now it should go ahead and carry on doing this and not get stuck there, asking the AI agent too much late on a Friday in the UK. So but yeah, as I was saying before, like some of these questions are around like expanding the scope of this. Like Liam said, we're only showing like a very small slice of like what's available in the platform for now. But also with this kind of workflow engineering, like this knowledge base that you build up over time can keep expanding. So as you do more of these things, if AI gets something wrong or you have like a model, like you say, where having to troubleshoot a model, as you're troubleshooting that, you can encode those learnings back into the knowledge base. So next time you come across those things, um, you've got it sorted out for next time. Okay, I'm not sure why that's thinking so long, but I've got a previous chat of this. Let's see if it's saved the history. No, it's not. That's ideal. Okay, I have to wait for this one to think a bit more then.
All right, got one more
Yeah,
question here
let's
that
go to
just
some
popped up.
questions. Not sure that's yeah.
So you mentioned skills. I'm curious how learning persists over time. As new cell data comes in, or as the agent hits a dead end, how does that feedback into future runs? Is it live memory, a curated skill, something in the database? And what does that path actually look like in practice?
Yeah. So the way we've been handling that is, yeah, through curated skills. So just increasing, sort of building on those skills in time, putting different gates in, um, and yeah, just building that knowledge into skills over time, so that that knowledge lives like within a specific tool pool. It depends like exactly where that is. Like depends on what kind of problem it came up against. Like because you can structure the skills in a way such that like some are kind of like higher level if you like, and then this decision makes you that flow down. You can be like quite targeted in where you put this feedback in to make sure that you get the right context at the right time.
Yeah, and another question here, which is basically, can the AI tell me where the gaps are in data? Like what
Yeah,
data don't I have that I need to have in order to get the result I want?
yeah, exactly. So part of that is this decision matrix that I was talking about in the slides, where it says like what kinds of models can it answer, what kind of questions, sorry, can it answer with kind of models. So I'm just going to start a new chat because this one seems to be on the go slow, but maybe we can ask it a question like that here. So yeah, what data would I need to answer a fast charge optimization problem? Okay, I see the problem. It's disconnected from Claude for some reason. Mhm. Right, here we go. Right, let's see if that's put the connection back up. Here we go. So yeah, we don't necessarily have to ask it like, very concrete things like, oh, how do I parameterize a model? We can ask it things about, there we go. So yeah, here we go. So it knows that in order to answer the question I've asked, I need to have a model that tells me about internal states. And so it's going to recommend that you try and build um, a physics-based model, like a DFN type model, and not an ECM. And so it's going to say, here's the data requirements. And so these kind of data requirements are things that you can build into your knowledge base. And then it's going to say, you need at least this. It'd also recommend this, and give you some recommendations. And then you can kind of chat with it and say like, oh, you know, so I could now say like, do I have all the data I need for the LG cell to make this model? Now, I've just seen the question about model specific skills. So right now we're just using like a single model for this whole thing, but like definitely like, yeah, within the future of optimizing this for token usage, like one of the questions earlier, I think, yeah, handing different tool calls off to different models, whether they're like high level or low level, is definitely the right call. And that's not happening right now. Okay. So that's it. Did I have all the data I needed on the LG cell to make the model that I wanted to make for this fast charging problem? And so it says, nope, not even close. So, and then tell you what data I have got within the platform already, and then what data is missing, and then what my paths forward are. So can I collect missing data? Can I ask a different question? Or can you go to literature and get some data that may be an appropriate substitution?
Last one here. How likely would a cell manufacturer provide the parameters or data to build a physics-based model?
Uh, Pretty
Depends
unlikely.
on the it depends on the manufacturer.
Yeah, it is. I mean, that's kind of like what the framework is for is whether you're someone who is working with a manufacturer who is willing to share data with you, then that's great because you get these parameters. Um, if not, then you can maybe collect your own data, whether you're doing your own teardowns or going to a third party, or maybe you're just building models that don't require a teardown. We've got some other approach. And so really that's like the power of the framework is that like given what you've got available to you and you understand what design decisions and engineering decisions you can make with models that you're actually able to build. Um,
Yeah, I mean there are two business cases, right? In this scenario, one is the manufacturer itself is using this for internal development, and we do see that. I would say depending on the sector, some let's call them like the product developers, for instance, like in the consumer electronics world, they wield a pretty heavy hand depending on who they are and their supply agreements, and they are able to get this information from the manufacturers abroad. We have seen that. So I think it is both like product and use case specific.
cool. Yeah, we've got a few minutes left if anyone has any last minute questions. But yeah, thanks very much for choosing to come on to our session. Hopefully it was interesting for you. And if you've got any like more questions for us, yeah, my email was in the slides, where you can find our contact details on our website. Always happy to answer more questions like this, give you a demo of platform of different aspects that you might be interested in. So yeah, please reach out.
One last one came in under the wire here. Within Ironworks, have you explored using the agent for test matrix optimization? So given a set of requirements or drive profiles, it suggests the most efficient test plan rather than the engineer having to define it up front.
That's not something we've got the agent doing right now, but it's definitely like within the scope of what we'd like to be doing.
Yeah.
And so like based
DOE
around
optimization. Yeah.
exactly, yeah. And so we've got a lot of the tools to do like as part of the parameterization, like we had questions about sensitivities and everything earlier on. So, coupling it together with that, we can really help to sort of slim down that DOE. Or if you've done like a course DOE, we can then understand like which areas are worth focusing on to improve the gaps in your model. Using those optimization tools and parameterization
Also a
tools
great
coupled with
lever
data.
in supply agreements, but that's a conversation for another day. So I think we are officially out of time.